Okay, welcome to the Structure of the Atom Notes Review. You should have already seen these in class, or unless you're working ahead, which is perfectly fine too. So just go ahead and get started. Atoms are the smallest particles of matter. There actually are smaller things called subatomic particles, but they themselves don't usually exist in nature. So we just typically consider the atom to be the smallest part of everything you see in nature. They're made up of three particles: the proton, the electron, and the neutron. Protons are positively charged. They're found in the nucleus. The prefix pro means positive, as in a pro and con. It's an easy way to remember it. P also starts with positive, starts with P, and so does proton. Easy little way to remember that. Each proton is given a charge of +1 or 1+, as you can see here. Electrons are the negatively charged subatomic particle. It's found in the space outside the nucleus, known as the electron cloud. Each electron has a charge of -1 or 1-. They have a very small mass compared to the protons and neutrons. They're the only subatomic particle that are found outside the nucleus itself. So it has its own special place called the electron cloud or the electron orbit. The neutron is the last of the particles. It is a neutrally charged subatomic particle. So the prefix neutral and neutra here means obviously the same thing. It means it has no charge. So as you'll see up here, protons +1, electrons -1. There is no plus or -1 here because this has no charge whatsoever. So basically weighs almost exactly the same as a proton. It's something very critical to pay attention to, especially when we get to calculating neutrons. So here you can see a couple of Bohr models. These are what's known as Bohr models. Bohr models are the representation of an atom where you draw orbits where the electrons go around and the protons and neutrons and the nucleus stay in the middle here. Let's see. You can tell which ones are which based on mass, charge, and location. Electrons are outside, they're -1. Protons are inside, +1. Neutrons are inside, no charge. Up here I wrote +1, -1 because, you know, easier to think about numerically. It really has no charge. Here's a couple more, like I was telling you earlier, Bohr models. Hydrogen being the simplest of the Bohr models. Red is protons, yellow is electrons. You'll notice hydrogen does not have a neutron. It's the only element on the periodic table that does not have a neutron. Helium here you see lithium. Lithium has 2 electron orbits because you can only hold 2 in the first shell, 8 in the second shell, and then 18 up to 18 in the third shell. Doesn't mean it has to have 2, doesn't mean it has to have 8, it just means it can hold up to that number. Here you see in sodium, 2 in the first, and you'll see 8 in the second ring here, or the second orbit, and it has 1 more out here. Why? Because it has 11 electrons. 2 plus 8 is 10, so you got to add another ring in order to get all your electrons in there. The atomic number, it's equal to the number of protons in an element. It's the number at the top when you look at a chemical symbol or an element on the periodic table. Atoms of different elements have different number of protons. That's very critical to understand because oxygen has 6 protons, nitrogen has 7 protons, or maybe oxygen has 8, I don't know. Anyway, the difference between one thing to another is the number of protons. So in a neutral atom, number of protons is equal to the number of electrons. And typically atoms are electrically neutral. Yes, and electrically is, you need to think about it in terms of electricity, kind of like static electricity, and you rub your feet on a carpet and shock somebody. Those are electrons flowing into you. But anyway, most atoms are neutral. They want to be neutral. They don't like to be charged. And you can typically, well, not even typically, but always, when you're using neutral atoms, you can go ape. Ape is atomic number is equal to number of protons, and it's also equal to the number of electrons. So you can go ape. Atomic number is equal to protons is equal to electrons. If you have 7, if the atomic number is 7, as in nitrogen, then it means it has 7 protons. Well, nitrogen usually has 7 electrons as well. Here you see the periodic table representation. Here's the atomic number, as I was mentioning earlier. It's at the top. Typically, the atomic mass number is always larger than the atomic number, and it's always a decimal unless it's already been rounded, which in most cases it won't. But it's always larger than the atomic number. Typically close to double, but not always, but typically. The atomic mass is technically the number of protons and neutrons inside of the nucleus. Because the electron has so little mass, it really doesn't factor in. So anyway, you add these things up. Well, if I know that I have 10 protons, which is the atomic number, if I know if I have 10 protons here, and I know the mass number is 20, because you round it, notice this, you get this by rounding the average. 20.17 is going to round to 20, so you go mass number minus atomic number is equal to number of neutrons. In this case, 10. It's not always the same. You have isotopes and ions of things, of different elements. I'll talk about this briefly, but most of you don't really need to know this. If you're taking this as an accelerated class, then it's certainly not going to hurt you to watch it, and it certainly won't hurt you to watch it as a regular science student. So anyway, let's get into isotopes. Isotopes are atoms of the same element have different numbers of neutrons. Here you see in the example below, it says hydrogen. One has 1 proton. This is also hydrogen because it has 1 proton. But this is what's called a isotope of hydrogen based on the fact that it has another neutron. If you remember, I was saying earlier that hydrogen is the only element that doesn't have neutrons. So in this case, it has a neutron, so the mass is different. You see the mass number here too. This is an isotope of hydrogen. This also is an isotope of hydrogen because it has 1 proton, 2 neutrons. Isotopes, the same element, have the same atomic number. That makes a lot of sense because the proton stays the same. You'll notice that. Remember what I was saying earlier. If you change the proton, you change the element. If I added another proton in here, then boom, I got helium because helium has 2 protons. So keep the protons the same, you change the neutrons. That's what's called an isotope. Ions, or atom has a what's called net positive or negative charge by gaining or losing electrons. Remember, electrons are negatively charged, and when you lose an electron, the atom becomes overall positive because typically they're balanced, as you recall. And if you look at the example here, it says this atom is neutral. It has 6 protons, 6 neutrons, 6 electrons. Now you'll notice the neutrons don't change because they have no charge. Ions have everything to do with charge. Now you'll see this atom. This atom is negatively charged because it has 5 protons and 6 electrons. That means it has 1 more electron than it does proton. So if these are all +1, so you have +1, 5 +1s, which means it has a +5 charge, positive charge. And the electrons here, you have 6. Well, you have -6 plus a +5 gives you an overall -1 charge. Therefore, it's negatively charged. It has more electrons than protons. Inversely, if you have more protons than electrons, then the atom is positively charged. So you can see that it has 6 protons, and then you see it has 5 electrons. So this has more positives than it does negatives, so it's overall what's called a positive ion. Here you see another Bohr model. Atomic number 6 has an atomic mass of 12. I know that it has an atomic mass of 12 because it has 6 protons and 6 neutrons. You add those together to get the atomic mass number. It shows again the Bohr model representation. 2 electrons in the first shell. It can't hold more than 2 on the first. It can hold 1, but it can't hold more than 2. And then the second shell can hold up to 8, but in this case we only have 4 more additional electrons because I already have these 2, and I only have, remember, if you go ape, atomic number is equal to protons equal to electrons. If I have 6 protons, that means I should have 6 electrons. Well, I have 2 on the first shell, and then I have 4. My remaining 4 go on the second shell. Can the second shell hold more? Yes, it can, but in this case, it doesn't need to. Always remember that when I say 2 on the first, 8 on the second, 18 on the third. That is a maximum number, which means it can hold less than that, right? So imagine your wallet, can hold 20 $1 bills, but you're kind of broke right now, and all you can really fit in it right now is 4 $1 bills. But you can hold more dollar bills, but in that case you just don't need to. So I don't know, kind of a weird comparison, I guess, but that looks to be all of the notes for the Adams review. I went through that kind of quick. I would advise you to possibly watch it again, or maybe slow it down, pause it, rewind it, if there's like a certain part you don't really understanding, as far as like maybe the atomic number or the mass number or so forth. So anyway, you got any further questions, let me know, and I'll see you in class.